We experience the physical world through structural resistance. We feel the friction of a synthetic sweater against our skin, or the rigidity of an iron bar on a bus. We usually only recognize electricity when it manifests as a discharge, like a spark from rubbing a wool cloth or a lightning strike during a thunderstorm. But the forces that hold solids together, the adhesive properties of glue, and the tension of a surface are all electrical in nature. They arise directly from the interactions between charged particles. Diving beneath the smooth surface of an object reveals a vast, mostly empty space. To understand why a solid feels solid, we have to look past the visible world and focus on the forces acting within this atomic lattice. Our objective is to build a quantitative model of these interactions, starting from the smallest possible unit, a single stationary point charge. Modeling our tangible reality requires adopting the strict mathematics of these invisible, suspended particles. Before these charges could be calculated, they had to be observed. Early researchers had to prove the existence of charge through physical evidence. They established a fundamental rule of polarity. There are two kinds of charges, and while like charges repel, unlike charges attract each other. This was demonstrated using the gold leaf electroscope. When a charged object touches the metal knob at the top, charge flows down the rod and onto the gold leaves at the bottom, causing them to diverge. This behavior defined two classes of matter: conductors, like metals, which allow charge to distribute across them, and insulators, like glass or plastic, which offer high resistance to the passage of electricity. While an electroscope proves that charge moves, creating a predictive model of matter requires moving from qualitative observation to a quantitative framework. To calculate the force between charges, we must first define their physical nature. Charge does not behave like a continuous fluid that can be divided infinitely. Instead, all free charges are integral multiples of a basic unit, denoted by E. This is the principle of quantization. Charge exists only in discrete, indivisible lumps. This grainy nature was first suggested by the laws of electrolysis discovered by Michael Faraday. It was later demonstrated in 1912 by Robert Millikan, who proved that charge is always an integer multiple of the basic unit. If charge is made of discrete grains, why does electricity feel like a smooth, continuous flow at our scale? Think of a dotted line. Up close, the individual points are distinct, but at a distance they blur together. Because a single coulomb contains roughly 6 quintillion electrons, the discrete steps of charge aren't visible at the macroscopic level. While the illusion of continuity works for everyday engineering, the model must account for discrete lumps in microscopic interactions. We can now calculate the interaction between two charges, known as the two-body problem. Charles Coulomb measured this interaction using a torsion balance. He found that the force between two point charges varies inversely with the square of the distance between them and is proportional to the product of their magnitudes. This gives us the standard algebraic equation, where the vacuum permittivity constant, epsilon naught, sets the physical scale in a vacuum. However, scalar algebra is insufficient here. A scalar equation can define the strength of the force, but forces act in specific three-dimensional directions. Placed in a coordinate system, position vectors r1 and r2 establish their locations from an origin. A displacement vector, r21, defines the distance pointing from the first charge to the second, while r12 provides the exact opposite direction. These unit vectors establish a precise line of action between the two particles. The final force vectors project along this line. If the charges are the same sign, they project away from each other. If they are opposite, they project inward. Using vector notation ensures the model correctly maps the space and automatically satisfies Newton's third law. The force on the first charge is equal and opposite to the force on the second. Vector notation solves the problem for two isolated charges. However, a real system, like an atomic lattice, contains a vast number of charges. We need a way to calculate the force on one single charge when it is surrounded by a dense cloud of other charges. We might assume that neighboring charges would interfere with or shield one another's fields. But the principle of superposition states that the force between any two charges is independent. It is completely unaffected by the presence of other charges in the vicinity. Consider two charges, Q1 and Q2. interacting in a void with a single force vector. When a third charge is introduced, the original interaction does not change. The initial vector remains as it was. Instead, a new interaction forms between charge 3 and charge 1. This independence allows us to use linear addition to solve for the total force. We simply apply the parallelogram law of addition to the individual vectors. The total force on a charge is the vector sum of all the forces exerted on it by every other charge in the system. In a system containing billions of charges, each individual interaction is calculated separately and added together to find the net trajectory. This principle turns the complex n-body problem into a solvable series of linear vector calculations. This model rests on 3 pillars: defining charge as discrete lumps, mapping the forces as spatial vectors, and summing those interactions through superposition. By summing these microscopic forces across trillions of particles, the grainy nature of charge disappears, and we arrive at the smooth, continuous forces we experience. The mechanical properties of the objects we touch are not separate from electricity. They are the result of invisible point charges interacting according to these exact mathematical laws.